Okay, so let's get started. Did any of you verify this expression, this identity? Okay, so it's coming out correct, right? This m square times identity.
Yes, ma'am.
Okay. So, so what today we will be doing is, so this solution we obtained for a particle which is at rest. Now we will get the solution for any arbitrary momentum for the particle. So we can do it in two ways. So, so let me tell you both the ways. So the
Ma'am, just a
yeah.
before starting it, I have a small doubt. Can I ask it now?
Yeah, yeah, sure.
In the previous lecture, you said that you defined that psi bar, right? Psi bar equal to psi dagger mu naught.
Yes.
Then you proved something. On the time, by using the commutative relation, you just get that mu naught to left side to right side of the exponential. How do you have done that? Actually, because it's exponential function, right? So
Just a moment. Let me get to
yeah,
that point here.
no, just come down.
Here I was
No,
taking.
down.
Okay, down. Okay.
Just a minute. Just a minute. Just a minute.
Sure.
No, I'm up. I'm sorry. I'm
Yeah,
sorry.
yeah,
Up.
yeah. Here, I
Ah,
guess.
here only. Yeah, here only.
Okay. So the point is that you are saying this is in the exponent we have this matrix. How am I taking this comma 0 to this side? Right?
Ah, exactly.
That's the doubt. So
Yeah.
okay. So let me just elaborate this point. So you can see that this is a matrix, but we can always expand it. So we will get identity minus I over 2 omega 0I is 0I minus square of that term divided by 2 factorial, sorry, plus minus I over 2 omega 0I is 0I square, and so on, gamma 0. So now we saw that A0I anti-commutes with this gamma 0. Is that correct? We saw this.
Ah, yes.
Yes. So that means A0I gamma 0 is minus gamma 0 is 0I. So what will happen to this equation? Lambda half dagger gamma 0 will be equal to, so yeah, so here you have A0I square, so this term 1 over 2 factorial, whatever is there, the coefficients, square of it, A0I square, and now you can multiply by that gamma 0. So this is A0I gamma 0, which will become plus I by 2 gamma 0 A0I, because I am interchanging the order, so it picks up on minus sign. Now here we have 2 S0I, so when I interchange, so when I take comma 0 to the left, it will not change its sign. because 2 times it's changing sign, so ultimately no change in sign. 2 factorial minus I over 2 omega 0 I is 0 I whole square plus so on. So every time 3 S0I appears, it will have a minus sign because it's exponential minus x, and you take the gamma 0 to the left, so there will be odd number of sign change, so that terms will become positive. So ultimately what you have is, now you can take gamma 0 common to the left, so identity plus I by 2 omega 0I is 0I plus 1 over 2 factorial. Now it's square term, so this minus sign will become plus, so on. So you get gamma 0 exponential plus I by 2 omega 0I is 0I, which is gamma 0 lambda half inverse. Is this clear? That's what we had here.
Yes, ma'am.
Any other questions?
No.
Okay. So let's start discussing the solution. So Dirac equation, let's write down first. Equal to 0. We are just starting, so this is a doubt from the last class, so we haven't started anything new yet. Okay, so just one doubt Dhanush had. So okay, how this yeah.
Yeah, before starting, actually, I was watching this previous lecture, so I was absent for that. So I got a doubt in lecture 5. So can you just go there? So just to confirm, just scroll up.
Scroll up, okay.
Yeah, here we are imposing a symmetry condition, right? For a Lorentz transformation, just down a bit, still down.
Lorentz transformation, yes, this one.
Yeah, no, this like on phi, there phi of phi prime x prime is equals to phi of x. That one.
Okay, here.
Yeah.
Yeah.
Yeah. So here we after imposing this we have written inverse, and just we have as x prime is dummy variable we have taken the prime, right?
So sorry, I didn't get your question. Would you repeat?
So here initially phi prime x prime is equals to written as phi of x.
Yes.
Now so here x have gone to x prime under some Lorentz transformation.
Yes, that
and now we have written for the x variable as x inverse of x mu. That means we have removed this prime because it's a dummy variable.
So yes, so here there is this mu x prime mu. So it's x prime mu. Phi prime and x prime mu should be equal to phi. So the field after the transformation evaluated at the new location should be equal to the original field before the transformation, evaluated at the point before the transformation. So that's it, that is this statement. So and it ensures that whatever transformation you have performed is a symmetry of your system. Now this x prime I am replacing by lambda mu nu x nu, and then so yeah, so this is lambda mu nu x nu. So this I can take inverse of it, like, So if you are getting confused for the 4 vector notation, you can see this simplest version. So here we have at each space-time location in 3 plus 1 dimension are given by this 4 vector x mu. If you have just a 1 dimension, then it's lambda x0, that is phi x0, which is same as phi prime at x0 is equal to phi evaluated at lambda inverse x0. So on both sides, so you can think of that you are replacing x0 by lambda inverse x0 on both sides. So then you will get this equation. So that this is exactly what this equation tells, and then here we have evaluated it infinitesimally.
Okay, is it like we have written x in terms of x prime in this scenario, and later for the third step we have just we have gone completely to the s prime frame, so we just made we just removed the prime there.
Yeah. Where are we removing? Here in the argument.
Then third step.
Sorry.
Yeah.
No. So here we have already replaced what is x prime in terms of x. So we have replaced just. We are not removing the dummy. X, that prime index. X prime is lambda, your Lorentz transformation matrix acting on x. So that is what we have replaced here. And then we are sort of saying that lambda x phi prime at lambda x equal to phi at x is equivalent to phi prime at x being equal to phi at lambda inverse x. Both are equivalent statement.
Okay. Yeah.
Okay. So let us start. So yeah, just briefly we will see what was the solution last time. So psi of x, we first confine ourselves to positive frequency solutions. So we saw that the Dirac equation, each component of the spinner, so we are suppressing the spinner index. Here A runs from 1 up to 4. And we saw that each of these components of the Dirac spinner satisfies the Klein-Gordon equation. So just like plane wave is a solution to Klein-Gordon equation, we expect the solution to Dirac equation should also be linear combination of plane waves, but we now also have to have a spinner with it. So we write the solution as u of x, which is the spinner, 4 component spinner, and exponential minus I p dot x. P0 is square root of p square plus m square, which is greater than 0. So it's the positive square root. Okay. So we are looking at positive frequency solutions. Okay. So this, when we substitute in the Dirac equation, we get gamma mu p mu minus m acting on the spinner u is equal to 0. So this is purely a matrix equation. And what was gamma mu? Gamma mu was 0, sigma bar mu 0. So this becomes minus m p dot sigma bar minus m. So it's in 2 by 2 form, all are multiplied by a 2 by 2. Here M is multiplied by 2 by 2 identity. This itself is a 2 by 2 matrix. So it suggests that we can write down the spinor as this. So UA is a 2-component spinor, UB is another 2-component spinor. Now we looked at the solution in the rest frame of reference. P mu was, so P square is equal to M square. So P0 square become M square if P vector equal to 0. So 0th component we can write M, other components are 0. So P dot sigma will become P0. So remember, sigma mu is identity, sigma 1, sigma 2, sigma 3. And sigma bar mu is identity, minus sigma 1, minus sigma 2, minus sigma 3. So P dot sigma is P0 identity plus 0. P0 is M, so M times identity, which means this equation become minus M, M. P dot sigma bar will also become P0 identity minus M. So that means you get UA equal to UB. So the solution, spinor, square root M is a normalization as per Peskin's book. We are following that normalization. So UP is square root M, xi, where xi is an arbitrary 2-component spinor. Okay. So this is what we discussed last time. Now we want to see what is the solution for arbitrary momentum. So this U is a function of P0 alone. So what do we need to do? We can do it in two ways. Either by using this identity that I asked you to verify last time, or we can always, from the rest frame, we can boost along a direction to get non-trivial momentum, right, in that frame of reference. So this is what is done in Peskin. So let's do that, and then we can also discuss the other method using this identity. So if we perform a boost, let's say along the third direction x3 by where eta is the parameter. So what will happen? So remember how a vector transforms under Lorentz transformation? It becomes exponential of minus I over 2 omega mu nu m mu nu rho sigma mu sigma, and we wrote down what is the vector representation for the generators of Lorentz transformation. I times eta mu rho delta nu sigma minus eta nu rho delta mu sigma. So we are performing boost along x3. Okay, so how would that transform the 4 vector that we have here? So these two, P1 and P2, will remain 0, but P3 will be some non-trivial P3, so that we can get by that equation. So what is So what is M03? M03 will be, from this equation we can obtain eta. This we did for M01. Similar thing will follow here. Can somebody tell me what will be M03? The matrix, the each of the entities in this matrix for M03.
It is boost along z direction, right?
Yeah.
So I have to see.
Yeah, so you can see this from this equation also, or otherwise, as you know, it how the each of the components change, like x0 prime becomes gamma, x0 minus beta x3, and so on. From that also you can figure out, or from this particular representation, as we said, let me just reiterate quickly. So it's 0 rho delta nu is 3 sigma minus eta nu rho delta mu is 3 sigma. So therefore yeah, so this is 0th row, 0th column. So rho 0, sigma 0, if you substitute, this becomes 0. Here also this will become 0. Right? So this is 0. Likewise, this is 0th row, second column, also be 0. This will also be 0. Now look at 0th row, that means row 0, but sigma 3. So this element will be 1. Okay, so all these elements will be 0. This element, this is rho equal to 3 and sigma equal to 0. That means you will get contribution due to this term. So it will become eta 3 3 delta 0 0. So this is 1 and this is minus 1 according to our convention. So this minus 1 will make it plus 1. So we have 1 0 0 0. Okay, so that's the generator. If you substitute it here, so remember this mu is getting contracted, and you know that omega mu is also antisymmetric under the exchange of mu. That's why we have 6 such elements and 6 such generators, because this is also antisymmetric under the exchange of mu. So omega 03 m03 is equal to omega 30 m30. So that means since this is according to Einstein's summation convention, this mu and nu are getting summed up. So when you have 03 m03, you also have omega 30 m30. So that's why we have divided by a 2 factor here. So that means the generator, when you replace in this vector, it will become, there is a I outside, so I will give you another minus sign which will make it plus, and this 2 will get cancelled out because you have 2 such terms. So therefore your vector, so we are only looking at this E and P3, because as you can see the P2 and P1, those are still 0. So this is exponential of, so we are looking at the 2 by 2 block. Okay, so 2 by 2 block, meaning only the, how would I say, I mean, so suppose we had boosted along the x1 direction, so then you would have 0 here, 1 and 0. So this block we would have worked with. So now we have here 1 and 1. So that block we are working with, the two-dimensional, 2 by 2 I mean. So exponential, let me know if anything is unclear. Exponential of 0. So omega parameter we are considering to be eta. So exponential 0, 1, 1, 0.
Can you explain the last step also then?
This one. So
Yeah, this one.
yeah, so instead of writing it this way, so we could have written it E 0, 0, P3 is equal to exponential of eta. So okay, so here we are just replacing what we have obtained. This particular thing we are replacing in this equation, how a vector transforms. So this is a 4 vector, right? This is P mu, 4 vector. So it has to transform under this vector representation. So so we could have written this equation like this. So 0, 0, 0, 1, 1, 0, 0, 0. Instead of doing that, we are just looking at the 0th component and 3rd component, which is equivalent because other components will be anyway 0. I mean, other components we are not interested in as of now. But ultimately the solution that we will get, we can write it down for arbitrary p. So, I mean, we could have written it this way, but that's not necessary. So therefore, sorry, did I answer your question?
No, from here to there, how you just transform from 4x1 matrix to 2x1 matrix? How you just change it? That's what my question is.
No, we are just looking at, it's not the transformation, we are just looking at the, okay, so I mean we can keep it this way also if you are uncomfortable with this. So yeah, so let's work with this 4 by 4, but ultimately we are interested in how E is related to M and how these vectors are related. So we can keep it this way, no problem. So so this will become, so just the way I was saying, we can expand this exponential, so 4 by 4 identity plus eta times that matrix plus eta square over 2 factorial. I just have to write more zeros now. Now square of that, if you do, then it will be plus dot 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 M0, 0, 0. So what do you have? The first element, when you add this, it will become 1 plus eta square over 2 factorial plus eta to the power 4 over 4 factorial plus so on. Okay. That is coming from this term and identity of, I mean first term of this identity and so on. then 0 0, this term will become eta plus eta cube over 3 factorial and so on. Eta plus eta cube over 3 factorial one plus
Ma'am, in diagonal axle there must be two ones.
in the diagonal there must be
From identity it is coming, na? In
oh, okay. Now, so this is cos hyperbolic eta sin hyperbolic eta sin hyperbolic eta so what do we get? M cos hyperbolic eta 0 0 m sin hyperbolic eta. So since I'm writing this, so it's P1 P2 you can see P1 P2 remains 0, but now E is m cos hyperbolic eta and P3 is m sin hyperbolic eta. Okay, any doubts? Okay, so yeah, so this is how the vector transforms. Now we have to see how the spinor transforms, right? Because we want to see the solution to the Dirac equation, which means we need to transform this spinor, and we know how a spinor transforms under boost. So now we need to use that equation. Now we have done this because it will be useful as we proceed. So now u of P will be, okay, so first of all, how does the spinor transform under Lorentz transformation? Psi x is equal to exponential of minus I over 2 omega mu nu is mu nu psi, so psi prime. So alpha beta psi beta. Okay, so this is how a spinor transforms. Now we are performing boost, so that means we know, right, what are the corresponding so boost will be when mu equal to 0 and nu equal to I, and we are now interested in 0 3. Yeah, so that means u of P will be exponential of minus I by 2 omega 0 I is 0 I. u p0, meaning the solution in the rest frame of reference that we have already obtained. Okay, can somebody remind me what is S0I? I forgot. Let me see. So S0I is I by 2 so this is S0I, which was I over 4 gamma 0 gamma I. So if we substitute it there, again that 2 will get cancelled out and we will be left with u of p being equal to exponential so there is another 2 coming from this S0I, so let me see, so half omega 03 is still eta minus sigma I 0 0 sigma I. So I square minus, that becomes plus, and we have this, right? So therefore this is equal to, sorry, sigma 3 of course. We are okay. So what is it? We can again expand it. Identity 4 by 4. Remember, these are 2 by 2 block diagonal matrices. I mean, this entire thing is, here there is a 2 by 2, here there is another 2 by 2, so it is a 4 by 4 matrix. Minus eta by 2 sigma 3 0 0 minus sigma 3 plus one over 2 factorial eta over 2 square. If I square that, sigma 3 square will be identity and that will also be identity, okay, plus so again minus eta over 2 whole cube 1 over 3 factorial. So if you cube that matrix, you will get back that matrix plus so on. Okay. So what is it then? First element is 1 coming from the 4 by 4 identity. So okay, we will write it in 2 by 2 block diagonal form. So 2 by 2 identity, then minus plus 1 over 2 factorial eta over 2 whole square plus similar term will come from the fifth term, which is 1 over 4 factorial eta over 2 whole to the power 4. Okay, one series will be like that. Another series is minus eta over 2 plus 1 over 3 factorial eta over 2 whole cube plus from the sixth term you will get 1 over 5 factorial eta over 2 whole to the power 5 and so on, which I am not writing. Okay, so that is the first term of that. Now this term will be 0, and you can guess that the term here will be similar, but there will be a plus in between because of this minus sign here. So that means the similar term, I'll just copy this. So plus in between.
In second term, sigma 3 is missing. Like first row, first column, second term, sigma 3.
Here?
No, like below you have written, yeah, sigma 3 is missing, I guess.
Oh, okay. Thanks. Yeah, sigma 3 is missing. Okay, so this is equal to cos hyperbolic eta over 2 minus sine hyperbolic eta over 2 times sigma 3. I hope I'm not missing anything else. 0, 0, then cos hyperbolic eta over 2 plus sine hyperbolic eta over 2 times sigma 3. Okay, sorry, I forgot to write the free solution. Sorry, I mean rest frame solution. So multiply by square root m xi. So this means square root m, what do we get? This entire thing minus sigma 3 sine hyperbolic eta by 2 xi cos hyperbolic eta over 2 plus sigma 3 sine hyperbolic eta over 2 xi. Okay, now we can further rewrite it as exponential, and yeah, so we had cos hyperbolic eta and sine hyperbolic eta obtained from the 4 vector. So we can replace this cos and sine in terms of E and P3. So cos hyperbolic is E over m and sine hyperbolic is P3 over m. Okay, now what is P dot sigma? P dot sigma is E P0, sorry, identity plus sigma mu was identity sigma. So P covariant, there will be a minus sign, minus sigma 1 P2 sigma 2 minus P3 sigma 3. We have seen P1 P2 are all 0, so then that means this is E minus P3 sigma 3. Okay, and P dot sigma bar is similarly plus P3 sigma 3. So therefore U of P P dot sigma I'm missing something. P dot sigma bar xi so now P dot sigma bar, that was m square so m is square root of P dot sigma bar. Sorry, let me just check this page. Okay. I cannot see what I'm missing in this way of doing it, but so let me start from this point and use another approach. Okay, so this was U of P. Now if I so cos hyperbolic eta over 2 we can write as exponential eta over 2 minus exponential minus eta over 2 divided by 2. This is how it is done in Peskin, but I'm not sure what is wrong here. Okay, I will worry about that later, but as of now let's do it this way. Sorry, here it will be plus minus eta over 2 by 2. So we can substitute that in U of P, square root m So eta over 2 plus minus sigma 3 minus exponential minus eta over 2 plus sigma 3 so therefore we have one minus sigma 3 over 2 1 plus sigma 3 over 2 1 plus sigma 3 over 2 1 minus sigma 3 over 2. Okay. Now what have we obtained? E was m times cos hyperbolic eta and P3 was m sin hyperbolic eta. But I substituted this only. Anyway, so E so m square is E square minus P3 square as we know, and from here exponential eta over 2 m sorry, this is a bit lengthy. So this we can substitute in that solution. Square root m so this is equal to, oh I see, okay, let me finish it, then I can say that. So E plus P3 over m, this square root m I can take inside, make it 1 over square root m, then 1 minus sigma 3 by 2 plus or what I can do is, this is m, so sorry, there is no by 2 here, this is just cos hyperbolic xi eta, so this is it. and so therefore square root m exponential of eta over 2 we can replace by square root e plus p3. Square root m exponential minus eta over 2 is square root e minus p3. Okay, so therefore this is square root e plus p3 plus square root e minus p3 1 plus sigma 3 by 2 xi square root e plus p3 1 plus sigma 3 over 2 plus square root e minus p3 1 minus sigma 3 by 2. Are there any questions if I have confused you at any step? And this is nothing but so therefore this is what this is equal to square root of e minus p3 xi square root of e plus p3 xi. Okay, and as we were saying that sigma dot p dot sigma is nothing but e minus, so this is a 2 by 2 matrix, this is e minus sigma 3 p3 which is equal to e minus p3 0 0 e minus p3. Sorry, this step is not correct. So p dot sigma square root is e minus p3 0 0 square root of e minus p3, and likewise p dot sigma bar will be p plus which means e plus p3 0 e minus p3. So when we take square root of a matrix, it just means you are taking square root of the diagonal elements. So therefore this is equal to So this particular element, if we look at, okay, this is equal to, so this is square root of e plus p3 0 0 0 1, okay, square root of e minus p3 1 0 0 0. So that means this is equal to square root of e minus p3 0 0 square root of e plus p3, which is nothing but square root of p dot sigma. Okay, and this particular element here, similarly, this is equal to e plus p3 0 0 0 0 0 0 square root of e minus p3. So this is square root of p dot sigma bar. Okay, so this is the solution for any arbitrary frame. Yeah. Do you want me to repeat any of the steps, or is everything clear to all of you?
Just slide down, ma'am. Just slide down.
Okay. This portion.
Yeah, that's it.
Yeah.
Just a minute. Can you please slide up? Just one page up.
Okay.
After this one.
After this one, okay. You want me to?
I said, yeah. Yeah, just fix here. Can you please explain the last two steps from here? How you just came to a conclusion UP is equal to this? Yeah.
This one?
Yeah.
Oh, okay. So I was first showing that what is p dot sigma. This is clear. P dot sigma.
Yes, ma'am.
Okay. So sigma was, so this p dot sigma, when I'm writing, it's p mu sigma mu. So sigma mu was identity, and then sigma 1, sigma 2, sigma 3. So sorry. So so therefore this is e times 2 by 2 identity minus, because p1 p2 both are 0, so minus sigma 3 p3. What is sigma 3? Sigma 3 is 1 0 0 minus 1, and e times identity 1 0 0 1. So, and there is a minus in between, so therefore you get this 2 by 2 matrix. That's p dot sigma. And then this is p dot sigma bar. Okay, similarly sigma bar mu was identity 2 by 2, and sigma 1, sorry, minus sigma 1, minus sigma 2, minus sigma 3. That was the definition. So therefore this is e plus sigma 3 p3. Okay, and when you take square root of a matrix, that means we are taking square root of the diagonal element. So if it is not diagonal, you should go to a diagonal you should diagonalize the matrix, and then square root of that matrix means square root of its diagonal elements. So here it's diagonal, so we don't need to worry about those. So p dot sigma bar is this. So square root of p dot sigma bar is this quantity. Now I have written this before explaining. So I was explaining it after writing that solution. So this particular element. So let me write it below maybe. So that particular element that we have. Sorry. So okay, let me just copy that down. So this was this was u of p. Okay, so therefore the first element here, this one, that is nothing but square root p dot sigma, because it's 1 minus sigma 3. So when I'm writing 1 minus sigma 3, it is obviously a 2 by 2 identity that is implied, because sigma 3 is a 2 by 2 matrix. So this 1 minus sigma 3 over 2 is this matrix, 1 plus sigma 3 over 2 is this matrix. So it gives you this, and this is nothing but square root of p dot sigma that I was explaining earlier. So therefore you can see that this element is square root of p dot sigma, and this element here is similarly square root of p dot sigma bar. So that's why this is the general solution.
Okay, ma'am.
Is that good?
Yeah.
Any other doubts before? So just let me just give me a few minutes. 1 minute. Just I want to see. I thought this would be easier. So we have a square root m in the denominator. Oh, I see where I'm missing. So here we have, okay, here we have eta over 2, and I was replacing cos hyperbolic eta, which was e over m. So that was the mistake. Okay. You see, so you cannot just replace this cos hyperbolic because it's eta over 2, and from the vector transformation what we have obtained, that from that we can relate cos hyperbolic eta. So it's better that we replace everything in terms of exponential eta and then find out what is exponential eta over 2 and then replace it the way I was doing later on. So here, okay, so let me just strike this portion or maybe rub it. Okay, I'll just rub it. This was not correct because it's cos hyperbolic eta over 2 and I was replacing cos. Okay, the other things are fine, I guess. Yeah, that is also fine. So okay. Okay, good. So we have then seen what is the Dirac solution for any arbitrary frame of reference. Okay, now the two possible basis choice. What's the time? Xi. So as I was telling last time when we did the rest frame solution, there are two possible choices for this xi. So we put another parameter s where s takes 1 and 2, where xi1 can be 1 0 and xi2 can be taken to be 0 1, because they transform like the like a two component spinner. So okay, so therefore, so what is u1 corresponding to xi1? It's square root p dot sigma 1 0 square root p dot sigma bar 1 0, which is equal to square root p dot sigma is that matrix E minus p3 0 0 square root E minus E plus p3. So this is E minus p3 0, and what is sigma v dot sigma bar? Square root E plus p3 E minus p3. So this is square root E plus p3 0. Okay. Likewise, u2 corresponding to xi2 will be 0 1. So this is equal to 0 square root E plus p3 0 square root of E minus p3. Okay. Now let's define the helicity operator. So what is helicity operator? It's defined as half of Si. So it's the projection of spin along the it's a projection of spin along the direction of the momentum. Okay, so this is sigma I 0 0 minus sigma I. So if you look at these two solutions that we have obtained, u1, so h u1, what will it be? u1 is this vector, so this is unit vector, so it's just showing the direction along which the momentum is, and so this is 1 minus 1 1 minus 1, right? That matrix corresponding to helicity operator. So you get half square root E minus p3 0 square root E plus p3 0. So that means you are getting back half u1. So it shows that u1 is the eigenvector of helicity operator with eigenvalue plus half, and this is called with helicity eigenvector of helicity operator likewise helicity on u2 this is equal to, as you can see, it's minus half 0 square root E plus p3 0 square root E minus p3. So it has so u2, okay, minus half u2. So u2 is eigenvector of helicity operator with eigenvalue minus half. These are respectively called left-handed and right-handed. So which one is which? I need to see. I think the plus half is called left-handed and minus is called right-handed. Yeah, I think that it's not written in my notes, but I think this is called left-handed and this is called right-handed. But you can check on Pesky. And one more thing is that the helicity is not a Lorentz invariant quantity because it depends on momentum. Here, the direction of the momentum. So you can always go to a Lorentz frame where the momentum can have a different direction, so the helicity can change. But helicity is only Lorentz invariant quantity for a massless object which moves at the speed of light. So now remember one thing, someone was asking me when I was writing that why I was calling it left-handed and right-handed. So we defined the while spinners as psi, we wrote it as psi L, psi R. I was calling psi L to be left-handed and psi R right-handed. Now remember, they satisfy the while equation for a massless particle. So for a massless particle, just recall what was the equation satisfied by this psi L and psi R. So I gamma mu del mu minus m psi equal to 0. If we write down it in the matrix notation, so gamma mu is sigma bar mu 0. So this becomes minus m I sigma dot del. Okay, when we are writing dot, it means it's a four-dimensional dot product when we are not putting any vector sign. So sigma bar dotted with del minus m psi L psi R equal to 0. So and when m is equal to 0, psi L and psi R, they remain decoupled. So this gives minus m psi L plus I sigma dot del acting on psi R equal to 0, and I sigma bar dot del minus m psi R equal to 0. For massless particle, we get what is called while equation. Okay, I sigma bar dot del. So this is called while equation. So the point is that the solution to the while equation to this have definite helicity because these are for massless particles. No matter which frame of reference you see, they have definite helicity, and this is why psi L is called left-handed while spinner and psi R is called right-handed while spinner. So this is why we this is just I wanted to point out, because when I was writing, someone was asking what is this handedness. Handedness is this helicity eigenvalue corresponding to this helicity operator. If it is plus, it's left-handed, minus right-handed. Okay, is everything?
So helicity basically says like what is the direction of the spin and the momentum.
Projection of the spin along the direction of the momentum.
Okay.
Yes.
And when both are opposite, it is right-handed.
Yeah, you are getting minus. Yeah.
Okay. Okay.
Yes. So, uh, okay, now what we can do is, yeah, so we will always choose the basis. So what was the solution to the Dirac equation? Let me just write it again. So us square root p dot sigma xi s square root p dot sigma bar xi s. Now we will always choose a basis such that xi s dagger is delta sr. Okay. Now it was so far positive frequency solution. Similarly, you can obtain the negative frequency solution, which means, so I comma mu del mu minus m psi of x equal to 0. This was your Dirac equation. Now we had chosen this in such a way that it give us positive frequency. Now if we choose a different spinner v of p exponential I p dot x, then it will be negative frequency solution, and for this again you can obtain similar solution. So if you replace this in the Dirac equation, now the matrix equation that you obtain is gamma mu p mu plus m acting on v of p equal to 0. So so let's say we are in rest frame of reference, then it will become m acting on, let's say VA VB is equal to 0. So you can see that in the rest frame of reference, the solution to negative frequency, solution to Dirac equation corresponding to negative frequency would be square root m eta minus eta. Okay. Now again, there will be two possible choices for any two component spinner, as we know from our quantum mechanics course. Any two component spinner, you can either take 1 0 or 0 1. So likewise we need to put a s in a parameter where s takes values 1 and 2. So this is the solution to Dirac equation for corresponding to negative frequency in a rest frame of reference. So the same, whatever we did, same line of calculations will go on, and you can obtain what is the solution for arbitrary frame of reference, and you will get, it's the same thing, square root of p dot sigma eta, but there will be a minus here, square root of p dot sigma bar. You can just do by yourself so that you are familiar with how to obtain that. Okay. Okay, so here again p0 is square root of p square plus m square, which is greater than 0. But we have interchanged the sign now. It was minus earlier, now it's plus. So that's why it's positive frequency now. Sorry, that's why it's negative frequency now, in contrast to positive frequency as earlier. Okay. Again, this basis we will choose in such a way that S eta R dagger eta S is delta RS. Okay. Now let's see the normalization of these spinors. What is U dagger R P okay, so remember what was U? So U dagger would be dagger square root of P dot sigma and square root of P dot sigma bar square root of p dot sigma so this gives p dot sigma plus p dot sigma bar okay. So, and what is it? If we add those two matrices, this is p dot sigma, so there is no square root. That means if we go back, where did I write it? So if we add these two, yeah, we will get 2e in the diagonal, right? We will get 2e in the diagonal. So this is 2e times 2 by 2 identity. And that is nothing but delta RS. Okay, so that's likewise you can check that VR dagger or in other words this is 2 times 0th component of the momentum delta RS. This also turns out to be the same thing. So what will it be? It will be the same thing because you will have a minus here, another minus here, but since you are taking this product, those two minus will give you plus in between, so you get the same thing for VR dagger VR. So that is 2EP delta RS. This is equal to 2 P0 delta RS. Now interestingly, if you take UR dagger P VS P, you will get 0. So let's just check this quickly. This is equal to xi R dagger square root P dot sigma xi R dagger square root P dot sigma bar. Okay, this is because square root of P dot sigma eta is I think this is because these two has to be orthogonal. But I'm not completely sure. I will confirm this in the next session. But this has to be 0. I'm not completely sure about this argument. I will confirm in the next session. Okay. Now one thing you note that this normalization depends on P0, but P0 depends on the frame of reference. So this normalization is not a Lorentz invariant concept. Lorentz invariant normalization would be U bar R, as we saw for Dirac spinor as well, US this if we perform, so this is u dagger gamma 0 us. Okay, so we can do this, like what is u r dagger gamma 0, this is equal to square root p dot sigma zero 1 1 0 okay, so therefore so what do we get? We get p dot square root of p dot sigma bar 2 times but if you remember that identity we derived, I mean I asked you to derive, this is m square, so this square root of this quantity is m and that is delta rs. Okay, so you can see this is now Lorentz invariant. Just let me check this one, how this becomes 0.
Ma'am, here eta and this xi both are forming different bases, right? Because each are used in each solution.
Of course,
So,
but I
so
can
inner product
always
be zero.
no, yeah, that's what I was thinking, but that's what I was thinking, that this has to be, this inner product has to be 0, but then I was thinking, isn't it that we can choose xi to be 0 1, let's say xi 1, and eta 1 to be 1 0. We can choose that also, so that's why I got confused while saying it, but I didn't think of it earlier. But maybe what you were saying is what I was also thinking, but I still need to think a little bit more. Maybe I can think about
Ma'am,
it.
but xi and eta both are used in different solutions. Like xi is used in one solution, and like we generally all the solutions must be orthogonal in, I think.
Yeah, that's what I'm also thinking, but then I was thinking the other way around. But okay, I'll confirm, but it should be 0. Positive, because this is positive frequency solution, that is negative frequency solution, so yeah, they should be orthogonal. Anyway, we'll come back to that point. I think there's no confusion, but okay. There is another identity which will be useful when we quantize the Dirac equation. So let's look at that identity. So these are, okay, so this is u bar r, u is, likewise if you derive v bar, you can check, this will be minus 2m, okay, just check it. And if we, okay, so let's look at the completeness relation. called completeness relation. Summation over S equal to 1 to 2. U U R P U dagger, same U bar, sorry. So this is equal to, let's derive this identity. This will be used many times. So we wrote U bar earlier, so it was dagger square root of P dot sigma bar square root of P dot sigma. Okay, so we have square root P dot sigma this is equal to summation over S P dot sigma bar P dot sigma P dot sigma bar So this is nothing but summation over S this identity will again be useful, that this is M square, so we can replace it here. So this is M and summation over S, so xi s dagger is a 2 by 2 identity. If you take 1 0 and 0 1, this will always be 2 by 2 identity, and that is what we need to choose because we are also considering the basis vectors in such a way that their inner product gives identity. So this is outer product, so you get 2 by 2 identity. So this is M P dot sigma P dot sigma bar M. Okay, and this is nothing but gamma dot P plus M. So this identity a similar identity is satisfied by the negative frequency solutions. Just it's gamma dot P minus M. Okay, should we start the quantization is what I'm thinking. It's 43. Okay. Are there any questions at this point?
Ma'am, and yeah, negative frequency is referred to negative energy solution.
Yes.
Okay.
Yes. Okay. So yeah. So then we can start. We can start maybe the quantization of Dirac field. I was planning to derive the Hamiltonian, but that will not happen. It will take time. So we'll do that next time. Yeah. Okay. So let's just write down the a little bit. We'll not derive Hamiltonian because that computation is also very lengthy. We'll do it next time, but let's just start a little bit. Sorry. Quantization. So and I would suggest you to just look at this derivation of the Dirac equation, the solution to Dirac equation for positive frequency, how we did, but try to do the same for the negative frequency solution by yourself. Then you will understand the calculation better. And in the denominator, if there is m, don't try to put square root of p dot sigma times p dot sigma bar. We are never doing that, remember. So it's like a 2 by 2 matrix you are writing in the denominator, which is, I think, not correct. So wherever we are replacing square root p dot sigma, it's in the numerator. So keep that in mind, and then just do the negative frequency solution by yourself by looking, after you understand this positive frequency, which you already have. So quantization of Dirac field, Dirac spinor or whatever. So yeah, so since now we are dealing with fermions, unlike the quantization procedure of a Klein-Gordon field, when we quantize the Dirac field, we need to incorporate anti-commutation relation. So now the Dirac field psi has to satisfy this anti-commutation relation. We can start from here in the next class, but just let me say a little bit, and all other anti-commutators vanish. So when we are writing dagger, it means we have already promoted our field to operator, and now we are imposing this anti-commutation relation, because if you try to start with commutation relation for the Dirac spinor, it's explained very elaborately in Peskin's book or any other lecture note if you find. If you start with commutation relation, then you will run into trouble, like Hamiltonian will be unbounded from below, and so on. So therefore we need to impose this anti-commutator for the theory to be sensible. Okay, and for this to be true, so let's write down the Dirac operator now in the operator notation. So this is just like the Klein-Gordon field, same convention. Same convention for this normalization. So u was the positive frequency solution, so that has to be multiplied by, we are now writing the Schrodinger picture operator, so that's why it depends on position only. We will, after we obtain the Hamiltonian, we will go to the Heisenberg picture. So the same thing we followed for the quantization of Klein-Gordon field as well. So then this is B is dagger, okay, and psi dagger. Now, okay, now if you remember, we also quantized the complex Klein-Gordon field. So when we quantized complex Klein-Gordon field, like for real Klein-Gordon field, we just had A and A dagger here. But when we went to quantize a complex Klein-Gordon field, then we had to consider a different operator here, if you remember. Or you can go back to section 3 or 4, I guess, and check. And now the spinors are assumed to be complex, so we must have two different operators. But note one more thing, now because of the polarization, the two component spinor can take any two linearly independent values, 0, 1 or 1, 0. So there is also this additional index S. So, so in principle we now have as if 4 creation operators, like A dagger S, S going from 1 to 2, likewise B dagger S, S going from 1 to 2. So psi dagger B dagger exponential minus I p dot x plus so in order for this anti-commutation relation to be true, this creation and annihilation operators should satisfy pi q okay, likewise and all other anti-commutators vanish.
So we have assumed the anti-commutation relationship for some particular spinor, and we have imposing that for satisfying that the operators must satisfy this one.
Say that again.
So like have we assumed like have we initially taken the anti-commutation spinors in such a way that
No, so okay, so let me reiterate. So I was saying that this, if you start with the quantizing Dirac field, just like you did the Klein-Gordon, you start with the commutation, and this is what we did for the Klein-Gordon also, right? If we had commutator, let's say, so that is the way we started quantizing our Klein-Gordon field phi. So if you start this way, then you can always expand your operator in terms of the positive frequency, negative frequency solutions with appropriate operators. Now, if you would have started commutation, then they also had to satisfy a commutation relation for that to be true, for this to be true. And then if you try to obtain the Hamiltonian, for that commutation relations for the creation and annihilation operators, you will get the Hamiltonian to be like a dagger a minus b dagger b. So you will end up having a negative sign in between. So, and it suggests that your Hamiltonian is unbounded from below. You can create this b particle as many as you want, and your Hamiltonian will go to minus infinity, which you don't want. And the way out is that this spinor you should start quantizing by this anti-commutation relation. Furthermore, we know that fermions, Pauli exclusion principle has to be satisfied by fermions. That will also be also be true if you consider this anti-commutator, because then your ASP whole square will be 0, because as I wrote here, all other anti-commutations vanish. So ASP prime will be 0. So you cannot have a particular two particles with same quantum number. That is also implied when you have this anti-commutation relation. So if you start with commutator, you will run into many troubles, and to get rid of all those troubles, we have to get back to this anti-commutation relation for the fermions or the Dirac spinor. Sorry, I don't know if I answered your question. Maybe you can repeat your question.
No, it's I got it.
Okay, so one thing you can do, try to so assume this two anti-commutation relations to be true, and then show that this holds. Okay, show this. So this is what we did for Klein-Gordon field when we quantized. Now you try this out, and then next class we will do this one, and then we can derive the Hamiltonian as well, and also we'll see many implications after we derive those quantities. Okay, so let us stop here. Are there any other questions?
Ma'am, can you go to the session where you have derived the generators, right, for Lorentz transformations?
Session 5, is it? No, 6. Yes. Here, yeah.
Just above. These are for spinors, just above.
Okay, for vector representation here, yes. So this is how, yeah. M12 is for rotation, about 1 to
Can you go more up? More up.
Yeah, this was, I think, for boost. This was vector representation, which we also used today, and then this was the.
Oh, okay. Ma'am, you have used this Noether's theorem, and then you have generated. That is in session 5. Yeah. Here. Just bit above. Bit above.
Yeah. Yes.
Still bit above.
Okay.
Yeah, here.
Huh.
So here you have just stay there, ma'am. Here you have written d phi in this way. We got this. Now how you have directly taken that into the Lagrangian part, like from d phi relation, how you have said the Lagrangian is changing in this particular way.
Oh, this is exactly what we did for the space-time transformation as well. So the point is that if the field phi transforms this way, the Lagrangian should also transform in a similar way. That's the argument. If you remember, when we derived the conserved current corresponding to time translation and space translation, there also, I think in section, just let me show you that, because that's a bit simple. So session 2 is it? This is okay here. So space-time translation we are talking about. So the phi transforms under space-time translation in this way, and we are assuming that the Lagrangian should transform in a similar way. I mean, if it at all changes by a total derivative, then it should have the similar transformation property then as that of the field, because the Lagrangian is made up of that fields only. So this is assumption, and then we proceed like, so the change in the Lagrangian will be that, I mean, we don't have the exact Lagrangian in our hand. We are deriving the stress energy tensor for an arbitrary Lagrangian, and if the field transforms in this way, then the Lagrangian should transform in that particular way. The same thing.
So we just assume, but Lagrangian couldn't be as complicated as it. So why it's necessarily transform in that way? Think of if it have the components of 5 to the power of 4 or something like that, then it could transform in something different way, right?
We are not saying, I mean, we are not taking the derivative of the Lagrangian, I mean the fields in the Lagrangian. We are saying it's, I mean, if the space-time translation is happening by xi mu, then the Lagrangian should also transform along the direction. It's like xi mu del mu of L, but we are not saying how what is happening to the Lagrangian. I mean, that's how I understand it, but
Okay, so if we think like the space-time is transformed x mu plus xi mu, then the field is translated in this particular way.
yeah, this is what, this is nothing. Okay,
So,
okay, so I can tell you this way. Okay, so yeah, so field phi is becoming phi of x mu plus xi mu, right? So this is, we can Taylor expand it, plus xi mu del mu phi. That's what we have done. Now xi is infinitesimal. That's why we retain up to first order in xi. Similarly, Lagrangian is a functional of the field phi, which has become phi of x mu plus xi mu. So if we Taylor expand this, it should also become Lagrangian of the field phi plus xi mu del mu of L. You can think of it that way. It's a Taylor expansion of the Lagrangian, and yeah, and we are retaining up to first order in xi because we are considering infinitesimal transformation.
Okay, yeah.
Good. Okay. Okay, great. Let's meet next week then.
Thank you, ma'am.
Bye. Yeah. Any questions? Oh, okay. Okay. I'll stop the recording.